Here's a tighter, more focused version of your script, trimmed to fit roughly a 6-minute narration while keeping the core ideas strong and compelling. For centuries, humanity has looked to the sky for answers, mapping constellations, writing equations, and building entire models to explain our place in the universe. Over time, we believed we were assembling a coherent picture, a cosmos governed by rules, predictable, structured, and ultimately understandable. But that picture is beginning to shift. The James Webb Space Telescope was designed to refine our understanding of the early universe, to provide clearer images and stronger confirmation of existing theories. Instead, it has revealed something far more unsettling: a universe that doesn't always behave as expected. One of Webb's key observation targets is Abell 2744, a massive galaxy cluster that acts as a natural gravitational lens. By bending and magnifying light from distant galaxies, it allows us to look deeper into cosmic history than ever before. And what we're seeing is surprising. Some of the earliest galaxies appear far more mature than they should be. According to standard models, galaxies this early in the universe should be small, chaotic, and still forming. Yet Webb has found galaxies that are massive, structured, and unexpectedly bright, suggesting they evolved much faster than predicted. The deeper we look, the stranger it gets. Across vast distances, galaxies seem to organize into large-scale patterns, clusters and arcs that stretch across millions of light-years. While gravity naturally creates structure over time, the scale and speed of these formations are pushing the limits of current simulations. Then there are the planets. Take HIP 65426b, a massive gas giant several times larger than Jupiter, orbiting far from a very young star. The system is only about 15 million years old. According to traditional planetary formation theories, there shouldn't have been enough time for such a planet to form, especially at such a distance. Scientists have proposed explanations. Perhaps it formed closer to its star and migrated outward, or gravitational interactions pushed it into place. These ideas are plausible, but they require very specific conditions. In other words, the planet isn't impossible, but it challenges what we thought was typical. Webb has also captured striking examples of gravitational lensing, including near-perfect Einstein rings, where light from a distant galaxy is bent into a luminous circle by a massive object in front of it. This effect, predicted by Albert Einstein, is well understood. But the precision of some of these alignments is extraordinary. Individually, rare alignments are expected. But as more are observed, scientists begin to look more closely at the underlying probabilities. On even larger scales, Webb is mapping the cosmic web, the vast network of filaments made of galaxies and dark matter that spans the universe. These structures were predicted, but in some regions, they appear unusually regular, with patterns that hint at deeper complexity. This brings us to one of the biggest mysteries in physics: dark matter. We can't see it directly, but we know it's there because of its gravitational influence. Now, some researchers are beginning to question whether dark matter behaves exactly as we assume, or if there's more to it than our current models suggest. And then there are the signals. Webb has detected transient bursts of light, some showing rhythmic, repeating patterns that don't neatly match known sources like pulsars or quasars. In at least one case, a signal repeated at fixed intervals before disappearing entirely. Instrument error has been ruled out, but no clear explanation has been found. To be clear, scientists are not claiming anything extraordinary like communication. The universe produces many unusual phenomena. But signals like these remind us how much we still don't understand. Perhaps most surprising is how quickly the early universe seems to have formed stars. Some galaxies appear to have undergone intense star formation just a few 100 million years after the Big Bang. Even more puzzling, their chemical compositions suggest a level of maturity that shouldn't have been possible so early. Does this mean our models are wrong? Not necessarily. It may mean that star formation was far more efficient than we thought, or that the early universe behaved in ways we're only beginning to understand. That's how science works. It doesn't collapse when faced with new data, it evolves. For generations, we imagined the early universe as a slow, gradual process. But Webb is revealing something different, a universe that forms structure rapidly, almost aggressively, where complexity emerges far earlier than expected. This isn't the end of our understanding. It's the expansion of it. The James Webb Space Telescope hasn't broken physics, but it has exposed the limits of our current models. It has shown us that the universe is capable of organizing itself faster, larger, and more elegantly than we predicted. And perhaps most importantly, it has reminded us of something fundamental: our knowledge is incomplete. Right now, scientists around the world are analyzing Webb's data, refining theories, running simulations, and searching for answers. New telescopes will join the effort. Observations will become more precise. And slowly, the picture will become clearer. But for now, we stand at the edge of discovery. For the first time, we can study the atmospheres of distant worlds, detecting molecules like water vapor, methane, and carbon dioxide. The search for life beyond Earth has entered a new era. If even microbial life exists elsewhere, it would change everything.